Hi there, and welcome to today's lesson for BCIT's Technology Teacher Education TTED5060 course. And today we're going to be talking about batteries for your bot and the different types of batteries and how you can connect them to your robot or really to any electronics project to try and make the most of the right technology and the right battery. Before we do, though, I just wanted to talk a little bit about this and put it into context. I've been working on redesigning my classic BoomBot design right here, and it's been powered by 4 AA's and one 9-volt battery for the logic. And we'll talk a little bit in this presentation about why I've got two different battery packs in there and how the current design is going to be capable of being modified so that you can run it off of 6 AA's instead of having two separate battery packs in there. And also we'll take a look at why when you're building your Tethered Mini Sumo robot, we're going to be running off 4 AA's, even though the little motors that you're running off of are designated 3-volt batteries, and this looks like you're going to have 6 volts right here. Wouldn't that be too much for your motors? And so anyway, we'll take a look at that and why it's not that bad of a thing. But we'll go through the PowerPoint and then we'll come back and I've got a couple of sample questions that we can work through right here so that you can get an idea of some typical questions that you might find. But anyway, here we go. Batteries for your bot. And you'll find throughout my presentations that I often put some references and links down here. And that's because I am not the be-all and end-all fount of knowledge when it comes to these things. I've picked up what I've learned somewhere. And there's a lot more out there to know. Today, we're going to talk about some of the basics here. Now, just a bit of background for those of you for whom Chemistry 11 or Chemistry 12 or whenever you did redox reactions was a little while ago, is batteries are all about chemistry. A lot of time in electronics class, we end up talking about physics, but batteries are chemistry, and they're based on something called an electrochemical cell. And typically, an electrochemical cell contains two half cells, and one half will perform a type of reaction known as an oxidation reaction, and the other side will do a reduction reaction. And basically, the difference is that your oxidation gives off electrons, and your reduction reaction absorbs electrons. So you've got this source of electrons and you've got a sink of electrons. And here's sort of a classic, image stolen from Wikipedia. You'll notice I've cited it right down here, and also by the link. Is that we've got a reaction happening over here and a reaction happening over here. This reaction on this side is the reduction reaction. It needs electrons in order to proceed. And over here we have an oxidation reaction. It needs to get rid of electrons in order for that to happen. And part of what's going on in there is that we've got this membrane going back and forth between the two of them that allows the ions, oxidized atoms, to move from one side to the other. And only those ions can move back and forth. And that completes the electrical path. Okay, so what you've got when we talk about different batteries is you're talking about the chemistry that makes the battery happen. So when you hear everybody getting excited about lithium batteries, that's because there's lithium in one of the reactions. One of your metal plates in here consists of lithium. When you talk about a nickel metal hydride battery in there, well, you've got nickel in there and it's reacting with metal hydrides. Lead acid battery, one of your plates is lead and your electrolyte is acid. And okay, well, alkaline batteries aren't really a great example. They're actually a variant on the carbon battery that was around before that in the typical battery size cells, and they just use an alkaline chemistry instead of an acidic chemistry to make for a more efficient battery, but we'll talk about that later on. But basically, when you're talking about the name of a type of battery, you're talking about the chemistry that's happening in that battery and the materials that are used to generate the reduction and oxidation reactions. Now, the alkaline battery is probably the most common battery that we use all the time. And when you go into Costco or wherever you go to buy your batteries and you buy a, DURACELL, double A or something like that, chances are you're buying an alkaline battery. Now, here's an alkaline battery right there. Now, inside this alkaline battery, the 9 volt, there's actually 6 different cells. We'll talk about that in just a moment. But this is probably better called the zinc manganese dioxide cell. And as I mentioned up above, it was invented by a Canadian, but of course they were working down in the United States at the time because, you can't be a success as a Canadian until you've gone down south of the border and proved yourself by taking over the capital or something like that. Whatever they do down there these days. So anyway, we've got a little cutaway of a battery right here, and you can see there's a whole bunch of different things going on in there. But batteries have anodes and cathodes. Okay, so there's our anode, and we've got our positive coming out the top. And where's separator cathode? There we go, manganese oxide cathode. That's the alkaline bit, manganese oxide is alkaline in there, and these two parts are going to react with each other. Now, there's 10 billion of these being produced each year. So when we have recycling places to drop off your batteries, and we do have battery recycling available at BCIT, it's really nice if you bring those batteries in and drop them in the battery recycling bin because they contain reusable, valuable metals and minerals in there that really don't need to end up in a landfill. 10, an individual battery is not very big, but 10 billion of those little things starts to become quite the pile. Now, like I say, there's two half reactions going on inside your battery, and the half reactions consist of zinc with a hydroxyl radical. You'll see this around quite a bit, the OH minus. It's basically a water molecule that's had one of the hydrogens knocked off there. And so when the hydrogen joins back in, it becomes H2O. And in the process, it's giving off some electrons. That reaction can't proceed until something else absorbs those electrons and they head over to the manganese side of the cell, and that gives off some hydroxyl ions as well. And what you'll see is that the two half reactions have a voltage at each end. Now, the voltage is determined by how badly that reaction wants to occur. Okay, so you can see that the reaction of the zinc plus the hydroxyl wants to occur with a positive voltage of 1.228 volts. This side, the manganese is not quite as reactive, only 0.15 volt. So what you're trying to do when you're designing a battery is try to put really reactive materials in there, because the more reactive the material, the higher voltage, higher potential, the more it wants to get rid of those darn electrons. And that's why lithium batteries have really become so awesome, is because lithium is pretty much one of the most, it is the most reactive metal that we have and one of the most reactive compounds that we have. It really wants to take part in a reaction. So you're going to get higher voltages off of a lithium reaction than you will off of a zinc reaction or a nickel reaction. So anyway, what happens is we've got these two half reactions, and when you add their voltages together, you get an overall potential of 1.43 volts. And we kind of round that off up to a 1.5 volts per cell that we say is the nominal voltage for an alkaline battery. And that's why a C cell will be 1.5 volts, a double A will be 1.5 volts, AAA will be 1.5 volts. Each one of those we count as a 1.5 volt battery. Doesn't matter how big they are because they've got the same reactions going on in the cell. Now, when you're reading up on batteries, you'll realize that alkaline batteries are a type of cell that we call a non-rechargeable, or in battery speak, a primary cell. And what happens is that when you discharge that battery, you might be damaging the structure of one of those components during discharge in a way that you can't repair by recharging it. You might produce gas, for instance, and the gas might have to fizz off. So now you've got less material in that battery when the reaction is all finished. So if you try to recharge something, some batteries it can happen, some batteries it can't. It depends on the type of the reaction and the type of material and how you've designed and built that battery. So if the structure of the battery is not compatible with recharging, or the chemistry of the battery is not compatible with recharging, you can try recharging it, but you're not likely to be satisfied with that experience. You've seen maybe some rechargeable alkalines where they've changed the structure of the alkaline to make it so that you can recharge them, or sorry, change the structure of the cell to make it so that you can recharge them, but they haven't changed the chemistry, and the chemistry is not really ideal for recharging. Now, our secondary cells, they can be recharged a number of times, and so nickel batteries, originally the nickel cadmium, and then we got rid of the cadmium because it's a heavy metal that we didn't want people to be putting in landfills. The European Union banned them, and then the rest of the world said, "Oh, that's a good idea. Hey, EU, way to go." The British said, of course, that's all crap. We want out, but never mind. Uh, Anyway, rechargeable secondary cells can be recharged multiple times, and all you do is you apply a voltage and you drive the reaction backwards, and you force those electrons to go in the opposite direction, and you force those ions to flow in the opposite direction, and everything's undone, and you put it back the way that it was originally. And depending on the particular cell, you can do this hundreds or thousands of times before the cell gets sick and tired of having its electrons go this way and that way and this way and that way. One of those cells that's a secondary cell that we use a lot in automotive, in robotics, and all sorts of applications is the lead acid cell. And it gets its name because it uses a lot of lead, which you'll know if you've picked up a lead acid battery, it's very dense. And separating the lead is we've got hydrogen, sorry, we've got sulfuric acid. I was going to say hydrogen sulfate, which is another word for it, but you've got sulfuric acid in there. And so at the negative plate, what you've got is you've got lead reacting with the aqueous solution of hydrogen, a part of the sulfuric acid right here. And that's giving you lead sulfate right here. Plus it's kicking off a hydrogen ion and 2 electrons. On the positive plate, though, you've got lead oxide over here, and it's also reacting with the hydrogen sulfate in here, and it's absorbing 3 of these hydrogen ions and 2 electrons to become PbSO4. You'll notice that it's absorbed 2 oxygens in the process, and it's given off some water right here. So your acid has got a little bit weaker as the battery has discharged, which, if you know when you do your density measurements down in the automotive shop to check the weight of your the density of your acid, that if you've got a lot of water in there, it's less dense than when it was acid, so your battery's more discharged. So overall reaction is the lead plus the lead oxide plus the sulfuric acid gives you lead sulfate plus some water. That's how come the density is dropping, and you're getting more water into that cell. Now, this overall reaction generates 2 volts per cell. So if you look at a car battery, which is a 12-volt battery, and we use a lot of 12-volt lead-acid batteries, whether for cars or for robots or things like that, you'll see cast into the plastic, you'll see 6 little ridges in there because you've got 6 cells all in series, one after each other, and each one gives 2 volts. So by the time you go through the battery, those 6 2-volt reactions all in series with each other add up to give you a total of 12 volts. In fact, the very word battery refers to an arrangement of more than one thing. So if you think about a battery of cannons or something like that, that means that you're not going into battle with just one cannon, you've got a battery of them. And same thing in the battery. When we talk about our AA battery packs right here, okay, This right here is a battery because it has multiple cells. This right here technically is not a battery because there's only one of it. This is a cell. This is an AA alkaline cell, and this is an AA battery, if you want to get pedantic about things. However, a 9-volt battery is a battery because within this battery are 6 alkaline cells, each generating 1.5 volts in series. So just like with the lead acid, you've got 6 cells in series to get your 12 volts because there's 2 volts per cell. 6 times 2 equals 12. With the alkaline battery, to get your 9-volt battery, you've got 6 cells, each putting out 1.5 volts. 6 times 1.5 gives you your 9. Hey, come on, it's exciting. I just told you that, that this thing that you've called a battery your entire life really isn't a battery. All right, now that's the chemistry in the reaction, and that's where your voltage comes from. And it doesn't matter really what you do, you're getting the same voltage per reaction regardless. You can heat things up a little bit. That maybe gets you a little bit higher voltage sometimes. So a warm battery will give you more voltage than a cold battery. There's a number of factors going on there. Most commonly, that reactions want to proceed faster when they're hot. Okay, so let's take a look at surface area though, because surface area makes a big difference. And when you think about the cutaways of those batteries, the reaction is occurring at the interface between those surfaces. So if you've got more surface, then you've got more reaction taking place. Not only that, but you might be able to store more charge in there because you've got more of that lead or more of that zinc exposed to the electrolyte, so you've got more material that can interact right in there. And more surface area means you can store more charge in the battery. So one of the things that battery manufacturers do to get more charge into their battery is that they will make the surfaces wavy or rippled or have some kind of complex surface so that they're not just one smooth flat sheet. So they try to increase the surface area on there. And that can end up making your batteries a bit more delicate. So if you drive the reaction too hard and discharge the battery too deeply, you can damage those delicate surfaces. So you've really got a trade-off between batteries that are designed for high current and high capacity and batteries that are designed for high durability. So when you're looking at your lead acid batteries, you'll often see ones referred to as deep cycle batteries that are intended for multiple deep discharges. Those aren't the batteries that you'd use in your car. Automotive batteries are really designed to maximize your cold cranking amps or your maximum current flow so that when you turn on that starter motor for a few very brief seconds, that starter motor just gets this massive kick of current and revs you up even when it's minus 40 out. However, if you leave your headlights on and walk away from your car and that battery drains all the way down to nothing, that can cause permanent damage to the battery. Okay, and that permanent damage comes in the form of lead sulfate forming on the surface of those plates. It's something called sulfation. Eventually, it will destroy the battery if you keep doing deep discharges to your lead acid battery because sulfation mainly happens while the battery is discharged. If it's fully topped up and ready to go, your battery is going to be happy. Now that's lead acid batteries. Lithium batteries, if you're going to store them for a long time, instead of storing them fully charged, store them at about 70% so that you don't damage those cells because different batteries have different chemistry and behave different ways. So if you're going to put a battery on a shelf for a long time, read about the best state of charge to leave it in. But for your lead acid batteries, which are still really commonly being used, recharge them immediately after use. Don't let them sit there discharged. Sulfation can set in. Now, just as I was mentioning, there's these types of batteries called deep cycle batteries, and then you've got your automotive batteries designed to maximize, the amount of current you can get out of there in one sudden hit. There's also ways of putting your lead acid batteries together, and one is classic that you'd see in automotive class with a liquid electrolyte. And you've got to keep those batteries upright. And so typically you'd see them in applications like a car because theoretically your car remains upright most of the time. And if your car is no longer upright, the fact that your battery spilled is probably not your biggest concern. Um, You'll also see them used in deep cycle storage batteries. So for instance, if you've got a power generating station and you want to run it for a few hours, save that power, or solar panels and you want to save that power to use at night, your deep cycle storage batteries will be able to absorb that power. And really, because these aren't being moved around, you don't have to worry about them being tipped. However, for mobile applications, motorcycles have started to use sealed lead acid batteries a bit more, robotics applications, and anywhere where you might just pick a battery up and carry it somewhere and not carry it upright, or where you're putting in an application where you might have to use it on its side, you're going to want something called a sealed lead acid battery so you don't have sulfuric acid spilling out all over yourself. And just one note on here, although you can use them directly upside down, don't charge them upside down. And you'll see them, they fit into two major categories. And really in school applications, you can kind of interchange them. You'll see gel cells where the sulfuric acid is gelled, or you'll see an absorbed glass mat, the AGM battery, where you've still got liquids in there, but it's already absorbed and soaked into usually like a fiberglass mat, so that if something gets tipped upside down, well, it doesn't really want to spill because it's already been absorbed by the fiberglass material. Now, lead acid batteries are, I say now, this is January 2021. We've definitely seen a trend to replace lead acid batteries with lithium batteries. The lithium material was originally deemed far too reactive to use in many battery applications, but it's so reactive that it's so good for batteries that commercial forces have really driven the development of lithium batteries, and they're so much safer, more reliable, longer lasting, and with higher capacity than they were even just 10 years ago. You're seeing lithium batteries in all sorts of applications that you wouldn't normally have seen them in 10 or 20 years ago, and I think we're going to see them in more applications going forward. And if you look at the periodic table, lithium is clearly the most reactive metal, pretty much the most reactive solid compound at room temperature, perhaps even. And that's why it makes a great battery material. Now, some lithium batteries you'll get are primary cells, so they're really designed that you buy the battery, you use it, and you recycle it when you're done. And depending on how they've put the chemistry together and what else they're reacting with it and what they're designing for, in that you can get somewhere between 1.5 up to 3.7 volts per cell. So 3.7 volts per cell, almost twice the voltage per cell that you get from lead acid, and considerably more than you'd get from an alkaline, manganese alkaline cell. However, the main application where we use lithium batteries and where we think about our lithium batteries is in the secondary cells. And there's a couple of common types that you'll see people talking about are the lithium ion batteries and the lithium polymer batteries. There's also a third one that's out there called the lithium uh, iron phosphate battery, LiFePO. And anyway, the PO4, if I recall. And the lithium iron phosphate batteries are kind of neat because although they have good energy storage, they can also be charged and discharged more frequently than some of these other batteries. They're less likely to burst into flame if something goes wrong, and they are what was the other advantage? They don't have quite the same energy density as the drop off. But anyway, Up until now, these have not been common in high school projects. They're slowly working their way in as the technology matures and as battery management systems get better at making sure the batteries don't burst into flame when they're charged or don't burst into flame if they're discharged too rapidly. So there's a couple of neat lithium technologies out there, and people are continuing to develop them. And of course, we can see the impact that they've had on the electric vehicle market. And you can forget all that because it's not going to be on the exam. I don't want you to forget it. It's interesting and useful background material. But what we are going to take a look at are some properties of the batteries that really are determined by their chemistry and how they're put together. So what we just had was kind of a primer for what comes next, which is the meat that I really want you to pay attention to. And this is your nominal voltage, which is kind of based on the chemistry, your internal resistance, which is based on the amount of surface area, the battery capacity, which is based on the amount of reactant and the surface area of the battery, your discharge and recharge rates, which is kind of based on the structure of the battery, and the cycle life, based on the chemistry and the structure of the battery. So, nominal voltage. When you hear someone talk about nominal voltage, this is the name of the battery. So these alkaline cells right here have a number stamped on them. And if I pop that out, somewhere on this cell, it says 1.5 volts. You probably can't focus on that right now on that screen, but anyway, trust me, it says 1.5 volts. You've seen it on batteries, and that is the nominal voltage. Doesn't always mean you're going to get 1.5 volts out of that cell. That's just what we've named that cell. We'll talk about why you don't always get exactly 1.5 volts out of the cell in just a minute. Obviously, part of it is that when you use up all the reactants, you get 0 volts out of it, but we'll move on. Nickel metal hydride, the most common non-exploding rechargeable cells that we use, put out 1.2 volts per cell. Okay, so you can do things with this that make things very useful. So for instance, your Arduinos like to run at 5 volts. Well, if you want to give them a nice voltage. Maybe don't give them 4 alkaline cells because that's 6 volts, which is more than 5 volts and could damage a sensitive microcontroller chip. But you could use 3. No, the math doesn't work on there. Sorry. That should be 4. Just a minute, right here. I'll go back. Anyway, this right here should say 4 nickel metal hydride cells at 1.2 volts per cell, gives you 4.8 volts, which is very close to your 5 volts and is safe to use with an Arduino. So if you're looking for a 5 volt source, maybe don't use 4 alkalines, use 4 nickel metal hydrides, and do your math when you're doing PowerPoint because that's... Anyway, 6 lead acid cells, however, will give you 12.6 volts per cell. So that, and in fact, if you charge them all the way up, as you'll know from looking at your car battery, you're going to get more than 6 volt, more than 12 volts out of your battery. It'll usually be around about 13.3, 13.4 when very fully charged, and you can be happy with that battery down into the 12 volt range. But if it starts to fall below that, you want to top it back up again. Anyway, even though the battery is actually closer to 13 volts when it's fully charged, we call it a 12 volt battery anyway, because, well, that's what we call them. Nominal voltage. It's not actually what the voltage is. The voltage differs from the nominal voltage. Nominal is just a name. Now, each battery also has internal resistance because it takes electrical power to force the electrons through the battery. Now, Yes, the battery is forcing the electrons through itself, but it would rather just have a few proceed through. That would move more easily than having a lot through. In fact, if you discharge a battery rapidly, you can feel the internal resistance because you'll feel the battery start to get warm. So a rapidly discharging battery will heat up because the electricity flowing through that battery is going to give off heat because the battery has resistance. It's acting like a resistor that is built right into the battery, which kind of is. And we call this internal resistance. And so what that means is the output voltage of your battery is going to drop. In other words, the apparent voltage coming out that you measure at the terminals will be less when you're under heavy current draw than when you have no current draw or a light current draw. And you'll notice this in cars when you go and turn the key to start the car, that the headlights dim when you run the starter motor. The starter motor is drawing, in some cases, hundreds of amps. The battery voltage drops off. There is now less current flow through your headlights because if you've got incandescent headlights in particular, the voltage is less going through there, so they're basically just resistors, so the current is less, and you've got less power coming out your headlights, and your headlights dim briefly when you start the car. Now, the actual internal resistance of a battery is going to depend on its cell size and the chemistry. But basically, larger cells have lower internal resistance. So if you want to draw a lot of current, get a bigger battery. So for instance, inside this little 9 volt, okay, there are 6 cells packed into there. So each of those cells is pretty tiny. So if you need to draw a lot of current, don't try drawing it from a 9 volt battery. It'll give you 9 volts, but with only a tiny little bit of current. As you start to draw more and more current, the internal resistance of this battery is going to drop your actual voltage down quite a bit. In fact, if you're going to draw a fair bit of current, you're better off on using a larger battery pack, okay? Because there's more surface area in there for the reactions to take place, more cross-sectional area for the electrons to flow through, and as a result, lower internal resistance. Now, as you discharge the battery, you're going to start running out of places on the surface plates for those reactions to take place. And you're going to see the internal resistance start to go up. However, you can decrease the internal resistance by heating the battery to a certain point. If you're boiling the sulfuric acid inside your car battery, that's probably a bad sign. But anybody who's lived in the north and has tried to start their car on a cold day knows that your battery really doesn't feel like doing work at minus 40. Okay, the reaction rate's gone down and the internal resistance has gone up. Now, just as when we put batteries in series, so right here, I've got 4 AA batteries all hooked up in series to give me 6 volts. We also add the internal resistance together because when you put resistors together in series, you add up their resistances as well. So you'll see that a little bit later on when we do some calculations, we'll say, well, we'll add up, 4 times 1.5 gives me 6 volts coming off here. But for my internal resistance, if each cell has an internal resistance of 1/10 of an ohm, because all of those cells are in series, I've got to add up the internal resistances. So I'm going to have 0.4 ohms as my total resistance for that battery pack. So internal resistance really does matter when you're using batteries under load. Now, battery capacity is another factor you have to take in mind, and this is usually measured in amp hours or milliamp hours. Basically, 1 amp hour is the ability to provide 1 amp of current at the nominal voltage of that battery for 1 hour. So a 1 amp hour battery would be able to theoretically give you 1 amp for 1 hour before it's discharged. A 2 amp hour battery could give you 2 amps for 1 hour, or 1 amp for 2 hours, but it would have twice the capacity of that battery. A 1 amp hour battery could also give you 2 amps for half an hour, because 2 times 1/2 still gives you 1. As you get to quicker and quicker discharges, we start to deviate from that formula. This is an approximation, and we'll talk a little bit about that as we get there. But so for instance, your 1 amp hour battery could, if you discharged it in 10 minutes, give you 10 amps of current. Ballpark, it probably wouldn't give you quite that much. Batteries don't like to be discharged rapidly. A battery, if you hooked it up and put a 5 amp load on it and it ran for half an hour, that would be 5 amps times 1/2 of an hour, 2.5 amp hour battery. And when we're dealing with our smaller batteries, we'll use milliamps and talk about milliamp hours. So a battery that can deliver 100 milliamps for 3 hours is a 300 milliamp hour battery. Inside my phone right here, I think the spec said I had a 4800 milliamp hour battery. So that would be the same as a 4.8 amp hour battery. Now keep in mind, there's only one cell in there, so my voltage on that battery is not all that high. So, I mean, the battery is, considering its size and weight, very powerful. But, if you had a 12-volt lead acid battery with similar milliamp hours, it would have a lot more power stored up because it would be a higher voltage battery with the same discharge capacity. And of course, your power is your current times your voltage. All right. So as I was saying, if you discharge something really rapidly, the capacity may go down. And this is another one right here that's going to pop up in about 10 years or so, because after repeated charging and discharging, the battery capacity will go down. So after you've had a Prius or a Tesla, or in my case, a Pacifica hybrid for a decade or so, that battery capacity is going to start to go down after all the repeated charges and discharges that you've put through it. It just won't store as much energy, and even rechargeable batteries do have a limited lifetime. Now, one way to extend the lifetime of your battery and how many times you can charge it and discharge it is to charge and discharge it slowly, okay? And the rate of battery discharge or charging is often referred to as a C factor, where it's the current that you're charging or discharging at relative to your battery capacity. So for instance, a 1000 milliamp hour battery, if you were going to charge it with a current of 2 amps, that would be 2 amps over the 1000 milliamp would give you a rate of 2C. So that means that you'd take about half an hour to charge. That's a pretty fast charging battery. The batteries we use in FIRST Robotics are 18 amp hour batteries, and we discharge them pretty rapidly. So it wouldn't be uncommon to draw 180 amps out of that battery. And if you did that, that would be a rate of 10C, and your battery would be dead in 1/10 of an hour, which is about 6 minutes. Okay, now it would likely be a little bit less than that. Batteries don't like rapid discharging. And quite frankly, if you discharge them that rapidly, you're not going to get the same life out of that battery as if you were to discharge it at 1C. When I say life, I both mean in terms of how long the battery stays charged for, but also the number of times you're going to be able to charge and discharge that battery before it starts to wear out. You'll discover that high C rates, because you're cramming so much current through the battery relative to its size, will, as a result of internal resistance, result in warm batteries. More so than when you're charging, because there you're driving the reaction backwards rather than when you're discharging the battery and you're driving it forwards. One of the things that I do recommend, just as an aside at this point, is that if your cell phone has rapid charging functions on it, and you want to get a long life out of your cell phone battery, turn off the rapid charge functions except for when you really need them. When you charge or discharge something rapidly, the batteries have to do a lot of work. And at a structural level, they can take tiny little bits of damage each time you do that. So if you don't need to fast charge your batteries, don't fast charge your batteries. Take it nice and slow and keep that C rate relatively low. Uh, your batteries will have more charge discharge cycles before their capacity starts to drop off. And this is what I'm talking about here with the battery cycle life. And each different battery or each different cell is going to have a rating from the manufacturer on the number of charge and discharge cycles before the capacity falls to 80% of the rated capacity. So if you've got a 1000 milliamp hour cell, when that battery can only store 1000, 80% of that will be 800 milliamp hours, you'll say that that battery has met its battery cycle life. Now, originally, a lot of batteries would drop down to that within a couple hundred cycles, which, if you think about cell phones and all that, a couple hundred charge cycles, if you charge your phone, if it discharges all the way and then charges all the way up once per day, a couple hundred charge cycles wouldn't see you through 1 year. But 1,000 charge cycles would see you through about 3 years, and quite often we see cell phone batteries start to fail after 3 years. If you think about automotive batteries for electric vehicles, where warranty periods for a lot of batteries extend out to 10 years, you start to run into some problems with that. Now, a couple of things that automotive manufacturers do to manage that is, first of all, they control the rate of charge. And they also control how low you can charge the battery and how high you can charge the battery. And, if you've got this inside your car or inside your cell phone, you don't manage the battery at all. The manufacturers take care of that for you. But if you've got your own batteries, you're building up a robot and all that, do read the manufacturer's directions about how the batteries should be stored, charged, and discharged if you want to maximize the cycle life and get the most value out of your battery. One of the neat things that automotive manufacturers do, so now I'll say Tesla, but I don't have their exact numbers and I don't have references to that. But what they'll do is when you buy the vehicle new, you won't use the entire milliamp hour capacity of the car's battery. It will look like you are using the entire battery because when you charge the car up, it will say that you're at 100%. But really, you're only going to be at somewhere around 80% of the theoretical maximum capacity of that battery. As you go out and you drive, your charge level will keep coming down until that little indicator on your dash says that your battery is at 0%. Now, even though it says at 0%, there is still charge left in that battery. In fact, it could be up to 20% of the battery's theoretical capacity. But the manufacturers, because they want to warranty their battery for 10 years, or however long, they want to make sure that the battery is managed very carefully. So you can then get down to 20% and charge back up to 80%. And you can do that a lot because you're not going into the top 20% or the bottom 20% of that battery's theoretical capacity. You're taking it a lot easier on the battery. You're avoiding the deep discharge and the really peaky high charge. And you're working in a very happy range where the battery's like, yeah, I'm not working that hard. I can do this forever. Couple of interesting things about this that come about is that there's been a number of stories now that I see go around where somebody in a Tesla or similar electric car with good online support and remote diagnostics has been stuck in traffic. The classic one is somebody's been out driving around all day doing their usual routine and they're planning to charge their car up when they get home. And this has actually happened to Tesla owners a couple of times. And there is a big roadblock, a humongous traffic jam, and they're stuck there and their headlights are on, their climate control is consuming energy, and their battery is slowly dwindling down. And where they used to have enough juice to get home, home. They're off on this long detour to get around the traffic now, and there's no charge stations anywhere nearby, and their battery's down to 1 or 2%, and they're starting to get panicky. And what you can actually do, at least in Tesla, is you can push the help button, you can call up the Tesla service desk and explain the situation. And on more than one occasion, the Tesla service desk has been able to say to their drivers, "Oh, not a problem. We've sent a one-time code to your car, and we've released the reserve capacity." And the little charge thing goes from 0 up to 20%, and there's this emergency reserve capacity to get you to a nearby charger. Now that means your battery is working a little bit harder than Tesla really wanted it to, but it gets you where you're going. The other thing the manufacturers do, which I think is quite clever when you think about their warranty and human psychology, is that the battery, as it gets older, is going to have a reduced storage capacity. Even with this gentle cycling from 20 to 80%, the top and the end are going to start coming down. Well, as the top and the end start coming down, now maybe they discharge to 15% and charge up to 85% of the theoretical capacity of the battery, so it still looks to the driver like they're getting the same range and same mileage off of their battery. Well, they are getting the same range and the same mileage. It's just they're working the battery a little bit harder. And eventually, when you reach the given number of cycle life of your battery and your capacities fall into 80% of your original, now they're no longer able to extend that capacity any further, and you're going to start to see degradation in your electric performance. But by that point, hopefully from their point of view, the warranty's expired and they've come up with a way to manufacture replacement battery packs, or you feel like you want a new car anyway. So anyway, just some interesting things that are going on in there. Battery management and looking after your batteries when you buy your own batteries can save you a lot of money. If you're using lead acid batteries for your robots, top them up every 6 months or so. If you're storing lithium batteries over the summer, top them up and then discharge them a little bit and then put them on the shelf. And if you're using cordless power tools, um, I've had this kill a couple of batteries for my cordless drills, is that if you leave the battery sitting on the charger, okay, what will happen is it will top the battery up and it will turn off the charger, and your battery will sit there and the battery will slowly discharge and the voltage will come down and the charger will say, oh, we've dropped to 90%, and it'll top it up again. And then the voltage will come down and then it'll top it up again. And if you leave your battery sitting on the charger for a couple of months, you might run your battery through all sorts of charge and discharge cycles completely unnecessarily. Charge your battery, take it off the charger, and just leave it sitting there. And it should be ready to go when you need it. And if it's not, then maybe you need to use your tools more often. All right, let's take a look at some of the specifications for some individual batteries. And here are some specs from the data sheet for the DURACELL copper top alkaline C cell. All right, and you can find data sheets for just about any battery that you're looking at. Google the name of the battery you're looking for, plus the word data sheet. And you'll find the internal resistance. Sometimes it'll be listed using the AC term for resistance, impedance. And so this battery right here has an internal resistance of 150 milliohms. Now it says here at 1 kilohertz because they're talking about impedance. This is the frequency. So if you were to discharge it using pulse width modulation, that at 1 kilohertz discharge frequency, you'd get 150 milliohms. Typical weight of your battery, typical volume, flat terminals, recommended storage temperature, operating temperature, okay, so pretty broad range, very useful batteries. And you'll see some interesting things on here. Now, for instance, here's the constant current discharge chart. So if I discharge this battery at a rate of 250 milliamps, so somewhere in here it tells me, right in here, it's going to give me the capacity of the battery, you will see that we start at 1.5 volts, and at 250 milliamps, it will take 24 hours to discharge that battery completely. And they say, it's completely discharged when you get down to 0.8 volts. Somewhere I usually cut them off somewhere around in here at 1 or 1.2. They stop being as useful to me. But on their chart, at 24 hours at 250 milliamps, which is a quarter of an amp, you've got 6 amp hours or 6,000 milliamp hours on there. If you discharge them faster, however, at 500 milliamps per cell, then you're going to come down here and you're only going to get a little over 8 hours, which is a capacity of just over 4,000 milliamp hours. Okay. Now down here, we've got some faster discharge rates because these are both pretty low discharge rates. If we were using something like this in our robot, we might be drawing current out of the battery at 2,000 milliamps. And so that is this line right here. And you might only get 45 minutes drawing the battery out that fast, okay, which is less than 2 amp hours of capacity on your battery. So how rapidly you discharge that battery really affects how much charge you can get out of that battery. The batteries have to work really hard to discharge really rapidly, and so they tire out more quickly, to put it in human terms. Okay, so interesting specs that you can find in data sheets for different batteries. Now, the C cell is considerably larger than the AA cell that we use. So let's see what we give up by going to the smaller, lighter battery. Okay, here you can see the constant current discharge rate, and here they only recommend discharging at a rate of up to 1,000 milliamps. We're going to discharge ours at a rate of 2. And as you can see right down here, there's 5 hours of service life. There's 2.5. Yeah, we're down well under 1 hour of maybe about 1 hour of service life there. And if we discharge it at 2,000 milliamp hours, we're down here at about half an hour of service life. So when we use a battery pack like this for driving our robot around, you're looking at maybe 30 minutes of continuous driving from that. And I think, as you'll discover, 30 minutes of continuous driving for most of these robots is actually quite a bit of driving. Now, if we switch over to a rechargeable nickel metal hydride cell, though, and you'll see that we've got a lower nominal voltage on here, but we've also got a much lower internal impedance. So this is an AA cell for the battery, and notice that it's only got a 20 milliohm resistance. Let's just pop back here. And where was our impedance? Right here. That alkaline battery had an internal resistance of 120 milliohms. So lower voltage, but due to the chemistry of the battery and the structure of the cell, way lower internal resistance. Okay, and what that means is we can discharge this battery harder, faster. So here it says the rated capacity is 2,500 milliamp hours, and they display high rate discharge a little differently. They're using these C terms before. So, sorry, the C terms that I mentioned earlier on. So a 1 C discharge rate on a 2,500 milliamp hour battery is 2.5 amps. So here's the curve for discharging at 2.5 amps. Comes down right here. And this says that you're going to get close to 1 hour of service life out of this battery. Now, I'd usually stop it right around here at 0.8 hours or the 48-minute mark on the battery. You can see that it goes through this nosedive right down here. And like I was saying with the lithium batteries in your car, why work them into this range where they're not happy? Okay, you can let the charger manage them on this end to make sure that you don't overcharge them, which can damage them. But why run for too long? But you're going to get this is at 2.5 amps. The battery lasts longer than the similar sized ALKALINE did at 2 amps. So in this case, for fast discharge applications, if you want a long service life, you may be better going with a high capacity nickel metal hydride battery than an alkaline battery, despite all those ads for the copper top being the longest lasting battery. Um, look at the data sheet and the numbers don't lie. Some of these rechargeable batteries are really good. Now, one of the other interesting things about that is that you'll say, well, but it's only a 1.2 volt battery. Well, when you put your batteries under load, remember that 1.2 volt or 1.5 volt is only a nominal voltage. Okay, so let's take a look at this. Hey, our alkaline batteries are 4 at 1.5 volts, gives me a 6 volt nominal voltage for this here battery pack. But if you've got nickel metal hydride batteries in there, you've only got 4.8 nominal volts. Sure looks better on the alkaline. But keep in mind the internal resistance values, because just as you've got 4 batteries in series and can sum up the voltages, you've got 4 batteries in series and need to sum up the internal resistances. So your alkaline batteries are going to give you nearly a half ohm of internal resistance, whereas your nickel metal hydride batteries won't even give you 1/10 of an ohm of internal resistance because they have different chemistry and different internal structure. Now, if we're drawing 2 amps of current, which is only 1 amp from each of our little motors, okay, 2 amps multiplied by 0.48 ohms is going to give you a 0.96 volt drop across the battery, giving you an output of 5 volts at the battery terminal. So even though our nominal voltage is 6 volts, we're going to get 5 volts at the terminal. For our nickel metal hydride batteries drawing 1 amp per motor, 2 amps times our total resistance of 0.08 ohms is going to give us a 1.16 volt drop. So we started at 4.8 volts nominal, we dropped 0.16, now we're at 4.64 volts, which is pretty darn close to 5 volts right here. So actually, when you start drawing current out of your batteries, their advantage in nominal voltage quickly disappears, and on a 4x AA battery pack, that advantage disappears somewhere around 2 amps, just over 2 amps, which is about the current that you'll typically be drawing from your Mini Sumo. So you may actually get, depending on the gear ratios and the torque loading on your motors, you may get actually better performance using nickel metal hydride, the lower nominal voltage battery, than the DURACELL ALKALINE copper tops that have been advertised so extensively, because the internal resistance of the nickel metal hydride battery is lower. The other advantage you get with the nickel metal hydride, as we saw on the battery capacity charts, is that you'll be able to run those batteries longer because they've got better capacity, and you'll be able to charge them back up again so you don't have to throw them out when you're done with them. So if you're charging and discharging your batteries, you can always have a fresh set of nickel metal hydrides available. The battery companies know this, of course, and also it's a little more complex to build a nickel metal hydride battery, so they charge you considerably more for the nickel metal hydride batteries. But if you use them a lot, probably better for the long run for the environment. One place where I do have to caution you about any of these battery uses is that inevitably in all of my classes, a student will bring to me a melted battery pack. And that is because they have shorted the leads on their battery. Now, it may be that they've built an aluminum robot and they have wires exposed, and they put the batteries down here, and the exposed wires touch the aluminum of the robot, and current did a short circuit from the positive lead to the negative lead and back to here. It may be that they had a 9-volt battery, and you'll notice that on my 9-volt battery, I always try to keep something over top of the terminals, because if I put the 9-volt battery in there with nothing over top of the terminals, then that's going to be shorting across the frames and heating up the battery, because I'll be drawing massive amounts of current because there's very little resistance in there. And destroying my battery. So if you get a short circuit, you can destroy not only your battery pack, but you can overheat the batteries to the point where the battery gets damaged and destroyed. So in that case, you really don't want to be using an expensive battery in there. In fact, something with a higher internal resistance is good because it's going to deliver less current when you short it out. Um, Another fun one to do with 9-volt batteries is throw them in your pocket when you've got change in your pocket and don't put anything over top of the terminals. Yeah, you get a warm pocket. You say, why is my pocket warm? You reach down there and you pull out a warm battery. Yeah, rarely do they ever catch on fire. No, hasn't happened to me. So anyway, just a few advantages trading off between alkaline and nickel metal hydride. You'll notice I'm not talking about the lithiums in here because if you short a lithium, it goes up in smoke. The lithium ferrous phosphate, not quite so much, but lithium batteries do have to have battery discharge management built into them so that you don't get a short circuit and end up igniting your batteries on fire, because putting out lithium battery fires is not something you want to be doing as a regular activity in your shop class. I haven't yet had an alkaline battery burst into flames on me, or a nickel metal hydride. Now, the batteries have voltage drops as well, but so do the wires that we run them through. And in electronics, especially when you're starting out in electronics, we just tell you that just assume that every trace on a circuit board, every wire in a circuit has no resistance. And we're not telling you the whole truth when we say that. We're simplifying to try and make the calculations get a bit easier. And most of the time, that simplification is fair and true and honest and accurate. But when we start to draw lots of current, particularly lots of current through a lighter gauge wire, we do start to get voltage drops in there. And when we're dealing with low voltage, high current signals like we are, well, relatively high current, 2 amps for some of the wire diameters that we're using on these Tethered Mini Sumo robots is pretty high current. We start to run into voltage drops in the wires. And in fact, I'm going to talk about the application in a Tethered Mini Sumo robot, but scale it up a bit to a first robotics competition robot, a 150-pound machine using a 12-volt, 18-amp-hour lead-acid battery. And we're looking at using cables in the 4, 6, and 8 gauge range right in here. Very heavy, very thick cables. And there's always a bit of a debate in robot design. Do you go for the thicker, heavier cable with the lower voltage drop, or do you keep your cables more flexible and slimmer and longer and easier to route? There are limits on how far you can go, of course, because if you draw too much current through too thin a cable, the cable will overheat, ignite its insulation on fire, or cause other problems in your circuit. But we're working on Tethered Mini Sumo robots right now, so we're going to take a look at the wires that we use to hook up our Tethered Mini Sumo robots. And so here is a wire gauge chart, and we're going to do some calculations to take a look at how internal resistance affects the voltage that comes to our motors, and also how the wire diameter comes to our motors. So, okay, I've swapped over screens here, and now you can see some lovely handwritten paperwork out here. And here's our robot down here. We've got 4 AA battery pack right in here. Okay, we're going to put alkaline batteries in here, but you can redo the calculation using nickel metal hydrides based on the information that we've given you. And so here's our 4 times AA, 6 volts nominal. And right up here, okay, so that's where I get my 6 volts from, 4 AAs at 1.5 volts per cell. I've kind of rounded off the internal resistance to 0.1 ohms per cell. So that means that I'm going to get a 4 AA battery, 6 volts nominal, but each one of these is going to have 0.1 ohm on it, giving me a total by the time everything goes there of 0.4 ohms internal resistance on that battery. All right, now the electricity is also going to have to travel through wires up to the controller. So when the electricity comes off of the robot, it comes up to the controller right here where I've got a couple of switches. And coming down this way, I'm going to have 1 amp traveling down that way. And that bat is going to come back from the motor. There's going to be 1 amp traveling that way. And on this side, I'm going to have 1 amp traveling down and 1 amp traveling back up. Now, all of that is coming off the battery. So the battery is going to have 2 amps flowing up this way into the controller, and then 2 amps flowing back down here. So we've got 2 amps that come up from the battery into the controller. We've got some switches on here that control the state of this motor and a switch that controls the state of that motor. And 1 amp will go off this way to drive that motor. 1 amp will go off and drive that motor. And then it'll go down to the motor. And then, of course, to complete our circuit, it needs to come back up here, and back up here, and back down to the battery. Okay, so that's our general layout right there. And for the purposes of our calculation, we're going just saying that each motor is drawing 1 amp. You could take a look at your motor power curve, and depending on your wheel diameter and your gear ratio and whether you're just driving or whether you're in a pitched pushing battle and what your coefficient of friction of the tire to the table surface is going to determine how much torque load there is on the battery, which determines how much current your motor is actually drawing. So number of factors at play in here. To simplify it, we've just said 1 amp to each motor. Okay, and we've also said that they're connected by 1.2 meter long wires. And we've said that these are 28 gauge wires with 0.2 ohms per meter, 200 milliohms per meter, okay, which means that each of those wires is going to equal 1.2 times 0.2 is 0.2, what's that going to be, 0.24 ohms from one side to the other. Okay, so you can think of each of these wires. Now, yes, they're wires, but because they're narrow diameter wires carrying relatively a lot of current to their diameter, they're also going to serve as resistors. Okay, so we've said that we've got 1 amp flowing up here, we've got 2 amps flowing up here. We can start by calculating the voltage drop in the battery. Okay, so the voltage drop in the battery, move that up so you can see better, is going to be 0.4 ohms times 2 amps, because both 2 amps are flowing through there. Okay, that is going to equal 0.8 volts. So we can say that we're going to have 6 volts, which is our nominal voltage, minus 0.8 volts equals 5.2 volts at the battery terminals right in here. Okie doke. Now, those numbers might be a little different than I used earlier on. I'm changing the numbers up because when you go online to do the questions related to this, you're going to see different numbers in there so that everybody gets a unique question. All right, now we want to take a look at how much does the voltage drop when the electricity comes up here. Okay, so if I've got 2 amps flowing in this line right here, okay, then the voltage drop that I'm going to see in that line, I've calculated that that line is a 0.24 ohm resistor. So 2 amps flowing through 0.24 ohms is going to be right along here, 0.24 ohms times 2 amps equals 0.48 volts. So now I started with 5.2 volts right here. I ended up using almost a half of that, almost a half a volt to get it up to the controller. Now the controller needs to push 1 amp down to this motor. So I can say this is going to be 1 amp times 0.24 volts, 0.24 ohms equals 0.24 volts. And that's pushed it down here. It's going to come back up this way. So coming back up this way, we've got 1 amp times our 0.24 ohm wire. It's going to come back up in here. And then it's going to join up with another amp coming down from this way. And I'm going to have 0.24 ohms in this wire times the 2 amps that are flowing through it. 0.48 volt drop right in there. So if I want to know what my voltage at the terminal on that motor is, okay, so if I was to put a multimeter across there while this motor was actually driving, what would it say? Okay, well, I lost voltage in the battery, so I'm down to 5.2 volts. Okay, I dropped 0.48 volts in the first wire. I dropped 0.24 volts in the second wire. It's lower in this one because I've only got half as much current through here. And of course, Ohm's law is V equals IR. Then I'm also losing voltage as the current has to come all the way back to the battery. So I'm losing 0.24 volts in the third wire. And then 0.48 volts in this fourth and final wire. And this is 0.48 volts again because this is combined up with the 1 amp coming down this way, and I've got twice as much current flowing through there, so bigger current drop. So if I add all of that up now, and we could round it off and just say half and quarter, but what the heck, I've got a calculator sitting right here, and move that so you don't get the light source reflected in there. Okay, so we've got 5.2 minus 0.48 minus 0.24 minus 0.24 minus 0.48 equals 3.76 volts actually acting at the motor. All the rest of that power has been lost, basically heating the battery pack and heating these wires up, forcing the electricity to flow through there. And what's kind of neat is, as I was saying at the beginning of our little lesson today, is that these are 3-volt motors, and our power curve that we look at for determining the torque is when the motor's running at 3 volts. And even though we're running them off of a 6-volt battery, we're probably only seeing close to 3 volts down at the motor. So all of those numbers that we looked at last week when we were discussing motor performance are probably pretty close to accurate. So just because you've got a 6-volt battery, don't assume that you're going to see 6 volts at your motor. There's voltage loss in all of these lines coming along here, and when you're dealing with high currents and low voltages, that voltage drop adds up really quickly, and you can see quite a bit less power coming out right here. Now, say you wanted to hot rod your Mini Sumo a little bit and get more power down to your motors. Well, how could you do that? Well, one way, of course, is to use a different type of battery? Well, for your Tethered Mini Sumo, I've limited you to 4 AA alkaline cells, but certainly when we get on to taking a look at the BoomBot, we can do things like upgrade to 6 cells. We can use nickel metal hydride cells, all sorts of things like that. But for just uniformity in here and to keep you from having to go out and buy a bunch of expensive rechargeable batteries, we're going to require 4 AA alkaline cells, commercially available, nothing really fancy. You're limited on that. You're going to get about 5.2 volts out here if you're drawing 2 amps. Now, one thing you could do is change your gear ratio so when you're in a pushing battle, you're not drawing as much current. Okay, because if you're not drawing as much current because you've got a different gear ratio and your motor's spinning at a higher speed, then you're not going to get as much voltage drop because the voltage drop is based on resistance, and V equals IR. You reduce your you reduce your current load, and you reduce your voltage drop. Now, the other thing you can do, of course, is reduce your resistance, and that means that you can reduce the resistance in these lines. Now, one way would be to switch to a heavier gauge wire. Problem with that is that as you go to a heavier gauge wire, that weighs on your Tethered Mini Sumo and reduces your maneuverability. You could probably go to a 26 gauge wire. I don't know if I've got any sitting around the shop. I do know I've got lots of 28 gauge ribbon cable sitting around the shop though. Wire that looks something like this. And we're really overworking it, running 2 amps through it over 1.2 meters, which is why we're getting that voltage drop in there. But it's nice and flexible, it's inexpensive, it's brightly colored, so it's easy to track which cables are hooked up where. So we're going to use it. But if you were to use 8 wires instead of just 6 wires, then you could double up on these wires right here. And if you doubled up on those wires right there, then each wire, instead of carrying 2 amps, would only be carrying 1 amp. And so each of those wires would only see a 0.24 volt drop, and you could gain an extra half volt at your motor just by thinking about how you're going to hook up your connections. Now, I've only talked about the wires. When you're dealing with bigger robots, of course, you've also got to connect those wires to things. In here, we've got fairly efficient little connections, but certainly when you're dealing with bigger robots and bigger currents, having quality terminals and keeping the terminals nice and clean and making good connections at your terminals is also really important for managing the voltage loss and heat generation in your wires. So that's why in first year electronics, we tell you to ignore the voltage drop in the wires, and we deal with very low current things. Just saves calculating a lot of things. When we start moving into robots, you do have to think about them a little bit more because in mobile applications, we tend to be using lower voltages because we're drawing things off of a battery, and we tend to have longer cable runs, particularly when we want to run a tether. You could of course, shorten this cable length. But if you shorten it down to a 10 centimeter lead, that really defeats the point of having a tether, and you're no longer building a Tethered Mini Sumo. I do require you to have at least a 1 meter cable lead coming off your robot. 1 meter's not so big, right? Gives you that little bit of flexibility so you can put it out there and drive around. And in our current COVID restrictions in the winter of 2021, that means that one driver can stand over here and the other driver can stand over there. And if you're 1 meter back and they're 1 meter back, your robots can be doing battle and you can maintain 2 meters of physical distancing and with your lovely masks on, be nice and safe. Right. Time for me to restock the coffee. Have a good day, and we'll see you in the lab.